compare, to find the smallest gap existing there. Group by group, min bits we discover, then sum them up. Power to power, power to power. Some discover, then sum them up. Power to power.
Hello friends, my name is Iris and this is CPP in Pajamas. Thank you for joining. Today we will solve question 3098 on LeetCode. Find the sum of subsequence powers. It is a hard question, but we will turn it into very easy. However, disclaimer, while my solution is easy to understand and to implement, it doesn't beat everyone else in runtime. For me, in these kind of questions, I go for simplicity. So if you are with me, let us begin. Find the sum of subsequence powers. You are given an integer array nums of length n and a positive integer k. The power of a subsequence is defined as the minimum absolute difference between any two elements in the subsequence. Return the sum of powers of all subsequences of nums which have length equal to k. Since the answer may be large, return it modulo 10 to the power of 9 plus 7. Let's look at examples. In the first example, the input array is 1, 2, 3, 4. K is 3. This means we need to extract all combinations, all subsequences of 3 elements out of the input array. These would be 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4, as listed here. In each of these subsequences, we need to find the power. So let's start with the first one. First, we need to find the differences in it. So they are between 1 and 2, it's 1, 1 and 3, it's 2, and 2 and 3, again 1. The minimal difference, the power, was 1. Here the differences are 2, 3, and 1. Power again is 1. Here 1, 3, and 2, again it's 1. And here 1, 2, and 1, again it's 1. In all 4 subsequences, the powers were 1. We sum them up to get a 4, which is our result. In the second example, the input array is 2, 2, and k is 2. Having the k the same as the length of the input array, we can only extract a single subsequence, the entire input array. The difference is 0, and that's our result. In the last example, the array is 4, 3, minus 1, k is 2, so the subsequences are 4 and 3, 4 and minus 1, 3 and minus 1, as listed here. Differences are 1, 5, and 4. We sum them up to get a 10, which is our result. Constraints. Length of the input array is between 2 elements to 50 inclusive. Every element is in the range between minus 10 to the power of 8 and 10 to the power of 8. Inclusive. K is between 2 and the entire length of the array. Okay, so here we can see that the acceptance rate and number of submissions is rather low. Let us turn this into easy on paper and then go to the code. To solve this question, let's divide it into 2 challenges. First challenge, how to efficiently discover the power of a single subsequence. Second challenge, how to extract all subsequences from the input array. So we start with the first challenge. Here is an array, here is k. In this case, we can only extract a single subsequence from the input array. So given this subsequence, how do we discover the power? First, we need to find all differences. These would be between 6 and 2, 6 and 5, 6 and 4, 2 and 5, 2 and 4, and 5 and 4. The minimal was 1, either between 6 and 5 or between 5 and 4. So the power is 1, but it took us many calculations to get to it. How will we make this more efficient? Correct, by sorting this. Once we sort it, it will be 2, 4, 5, and 6. Now that it is sorted, the only difference we need to calculate for every index is between it and the immediate neighboring index to it, because that's the smallest gap we will find. The further we go, the gaps will grow since it is sorted. So we only need to calculate the differences between 4 and 2, 5 and 4, and 6 and 5. That's it. And just as before, the minimal is 1, between 5 and 4, or 6 and 5. Just many less calculations to get to it. So this concludes the first challenge. To efficiently discover the power of a single subsequence, it needs to be sorted. So if we sort our entire input array just once, then all the subsequences we will extract from it will already be sorted. Wonderful. Let's move on to the second challenge, and for it I'm changing k to 3. So we can have multiple subsequences. How do we discover them? Well, we can say, how do we extract them? Well, we can say that in every subsequence, every index either participates in the subsequence or doesn't participate. In this example, in every subsequence, exactly 3 elements participate and one of them doesn't. But which one? That keeps changing. So the immediate intuition for such a thing is to use bits, right? To have an integer value that would run from 0, where all bits are off, until, well, in this case, 16 excluding, 0 including, 16 excluding, because in 15 all bits are on. And in every value that has exactly k bits on, this represents a subsequence. If there are k bits on, we just extract the indexes that correspond to the indexes that are on, and they are our subsequence. While this might be efficient for a small array, our array might have up to 50 elements, in which case we need to run until 2 to the power of 50. Not like here, 2 to the power of 4. So running up to 2 to the power of 50, and every time checking if the value has exactly k bits that are on. That just won't work. It will take way too long. So what would work? What's a better solution? Exactly, a recursion. We will have a recursion. Every call to the recursion will work on a single index, and it will either have it participate in the subsequence that we're building or not participate. What will be the work in the recursion? Simply call the recursion again to work on the next index, having the current index either first participate, and then not participate in the subsequence that we're building. The call to the recursion to work on the next index will do the same. It will call the recursion to work on the next index, having our next index first participate, then not participate. This way we will cover all options. Let us have a dry run on this example and see how it works. What are the parameters to the recursion? What does it need to know? Well, it needs to know the index on which it's working. It also needs to know the index of the closest neighboring index, that is also participating in the subsequence that we're building, because the difference between them is the only difference we calculate for the current index, just between it and the closest index that is participating, of course. This difference, the current difference, will compete against the best difference that we have found so far amongst indexes that participate in the subsequence. So this is the minimum difference found so far. And the last parameter that we need is k. Current k. How many more elements do we need to complete a subsequence? So let us have a dry run. We have our input array sorted. We first call the recursion to work on index 0. What is the previous participating index? There is none. So let's say -1 to denote illegal index. Current k, at this point, all three are required. The minimum difference found so far amongst participating indexes, there is none yet. So let's say the maximum of int, so that any difference will be lower than it and defeat it. So now we are in the recursion. Before doing the work, of course, we need to check the stop conditions to see if we need to fold or to work. So we have three questions to ask. First, what is k? Do we still need elements to complete a subsequence, or is it completed? Well, k is 3, we still need 3 more. Second question, is the current index in range? Definitely it is in range. Third question, given the current index, what is the current n? How many more elements do we have from it, including until the end of the array? Well, 4. Given this, do we have a chance to satisfy the request for current k more elements? Yeah, it's just 3. So given the answers to all these 3 questions, we see that we need to do the work. So the work, as we said, is calling the recursion again to work on the next index, first with us participating and then with us not participating. So let's first participate and call the recursion. So it will work on the next index. What's previous participating? Well, it's us. What's the current k there? It goes down to 2 because we are participating. And minimum diff found so far? Well, since we need to compete here with the difference that we received, but since we don't have any previous participating index, there is no current diff to discover here. So we just send exactly what we received. We did not compete with it. Okay, so we're in the recursion. Let's check. Okay, 2 more needed. Are we in range? Yes. Current n is 3. We will be able to supply 2 more elements to complete the k. So we're good. Let's do the work. We call the recursion again, first with us participating. So it will work on the next index. Previous participating is s. K goes down to 1. And previous minimum difference found so far, well, let's see here if we can compete with what was given to us. Well, we're index 1 and the previous participating is 0. The difference between us is 2. It's smaller, it's better than what we received. So now 2 is the minimum difference found so far. So this is what we sent to the recursion. So we're here. Let's check. Okay, another element needed. Are we in range? Yes. Current n, 2, so we will be able to satisfy the request for another element. Let's do the work. We call the recursion. It will work on the next index. Previous participating is s. K goes down to 0. And minimum diff, well, let's see if we can compete if what we received. We're index 2. Previous participating is index 1. The difference is 1. It's better than what we received. So now that's the minimum difference found amongst participating indexes. So we're here. Let's check. Well, now k is 0. This means a subsequence has been completed. We don't need to work. We just return the minimum difference that was found for it. Our first power. We return it to our caller, which will sum it up and fold. So now we're back here. We have finished participating, so now we need to not participate and call the recursion to work on the next index. Now the previous participating is not us. Now we are not participating. It's what was given to us. Same for k. Same for best difference. We are now not competing. So now we're in the recursion. Let's check. K, another element is needed. We are in range. We will be able to satisfy the request for 1 more element. Great, let's do the work. Call the recursion. First with us participating. It will work on the next index. Previous participating us. K goes down to 0. And difference, let's see if we can beat what we received. We're index 3. Previous participating index 1. Difference between us is 2. It's just as we received. Best difference remains 2. We're here, let's check. K is down to 0. A subsequence has been completed. It's our second subsequence. We just fold back, returning the power that was found for it. It's 2. To our caller, which will sum it up. Let's fold. So we're back here, finished participating. Let's now not participate and call the recursion to work on the next index. Previous participating, now it's not us, it's what we received. Same as K, same as minimum diff found so far. We're in the recursion. Let's check, K, another element is still needed. Index is now not in range. We are out of range. Given the fact that we are out of range and another element is still needed, we won't be able to complete a subsequence. There won't be any power here. So we just fold, returning 0. Let's return it to our caller, which will sum it up. It doesn't change anything. And fold. Well, we're back here. Finished participating, finished not participating. We can fold, return the sum of powers that we found to our caller, which will sum it up. So this becomes 3. Let's fold. We're back here. Finished participating and not participating. Let's return the sum of powers to our caller, which will sum it up, and fold. We're back here. We have finished participating. Now let's not participate and call the recursion to work on the next index. Previous participating as we received, K as we received. Minimum difference found so far as we received. We're in the recursion, let's check. 2 more needed, we are in range, current n is 2, so we will be able to satisfy the request for K more elements, 2 more. Let's work, call the recursion again. First with us participating to work on the next index. So previous participating is us. K goes down to 1. And difference, let's compete with this. We're 2, previous participating is 0, difference is 3. It's better than what we received as the minimum so far. So let's send it, 3. We're here, let's check. K, another one is needed. We are in range. We do have enough elements to complete subsequence. Let's do the work. Let's call the recursion again. First with us participating. It will work on the next index. Previous participating is us. K goes down to 0. Minimum diff found so far, well, let's see. We're index 3. Previous participating is 2. Our difference is 1. It's better than what we received as the best difference. So now 1 is the minimum. Let's send it. We're in the recursion. Let's check. K now is 0. Another subsequence has been successfully completed. We just fold, returning its power to our caller, which will sum it up. Let's fold. So we're back here, finished participating. Now we need to not participate, call the recursion to work on the next index. Previous participating, it's not us, it's what we received. Okay, no change. Minimum, no change. As we received. So now we're here, let's check. Another element needed, but again as before, we are out of range. Another element is needed, but we don't have anywhere to get it. We are out of range. A subsequence will not be completed. We fold, we return 0 to be summed up here, causing no change. Let's fold. So we're back here, finished participating and not participating. Let's fold, return to our caller. We're back here, finished participating. Let us now not participate. Call the recursion again to work on this next index, which is 3. Previous participating as we got. No change from what we got. Now we are in the recursion. Let's check. Okay, 2 more are needed. Are we in range? Yes, we are. However, and this is new in our dry run, we won't be able to satisfy the request for k more elements. Current n is 1, because we're here, we only have 1 more element, including current index. But 2 more are needed. We won't have anywhere to get them from. So, even though we are in range, we won't be able, even if we participate, to gather everything that we need to complete the subsequence. So already here, we can fold returning 0. We will not succeed building a subsequence, even with us participating. So we just return a 0 to our caller, which will sum it up and fold immediately. So we're back here, finished participating and not participating. Let's return the sum of powers that we collected to our caller, which will sum it up and fold. We're back here, finished participating and not participating. Let's return the sum of powers to our caller and fold. We're here at index 0, which is finished participating. Now it needs to not participate. And again, call the recursion to work on the next index, 1. Here, I think I can stop now because you can already see how it goes. We will now just be able to complete the subsequence of all these 3, 4, 5, and 6 here, indexes 1, 2, and 3, participating. And after that, again, we will not have enough. The current n won't be big enough, but I'm going to stop here because you understood all scenarios that we just have another power here, so it will be 5 altogether. This will conclude it, but I'm skipping it. We understood all the scenarios that we may encounter in our algorithm. We have a recursion that will work on the sorted array. Every call to the recursion will work on a single index, and it will first check if it needs to work, and if it does, it will just call the recursion twice again, once for that index participating, and then once for it not participating. The stop conditions are checking if more elements are still needed to complete the subsequence, and if we are in range, and the current n comparing to how many more elements we need. That's it. I think we're definitely ready to write the code, right? So here we have a main that calls a test function with various test cases. When we run them, then up to here, up to this test case, it will work beautifully. Here we will get a TLE. So we're going to write our code in 2 phases. In phase 1, we'll write the algorithm naively, as seen on paper. In the second phase, we will add an optimization in the form of memoization. And that will solve the TLE. Because what actually happens here? Well, take a look at this test case. The array has 50 elements and k is 37. Essentially what we're doing here is choosing all combinations of 37 elements out of 50 elements. 37 elements, that's so much recursion, and there are so many different combinations. The number of combinations, if we want to see the formula, is the number of combinations for m elements out of n elements. Well, in this question we call it k, so let's say k out of n is factorial of n divided by factorial of k multiplied by factorial of n minus k. That's many combinations. If you want to understand the formula, why it's like this, I'm referring you to this excellent explanation by this user. Very clear and simple explanation. Pause and read it. Then come back. So this is the number of combinations. And in each one there is so much recursion where the k is big. So for this we will need a memoization to not repeat recursions that we have already had. Okay, so that's in the second phase. So let us start naively. Okay, here is the signature from LeetCode. First, we sort the input array. Here we will declare memoization in the second phase. For now, let's just call the recursion and return what it returns to us. It will work on index 0, previous participating is none, k, and best difference found so far, int max. Okay. Returning the sum of powers, the recursion. So first, let's check the stop conditions. If a subsequence has been completed, return its power. Else, let's declare a variable current n. What happens when index goes to out of range? When index goes to out of range, that it's when it equals the size of the array, right? So when it happens, the current n will be 0. If n is not 0, it means we're not out of range. We still have elements. This means we can simply ask so if current n is smaller than k, it means we will not be able to satisfy the request for k more elements. Also, if we pass this line, it means that either n is bigger than or equal to k, which means it's necessarily above 0, because when k was 0, we returned. So if we're here, n is definitely above 0, meaning we did not go to out of range. So now that we have answered these questions, our stop conditions, we can do the work. So we can call the recursion twice. Sum of powers receive. It will work on the next index. Previous participating is us. So k goes down by 1. And now we compete with the best difference that we receive by calculating the difference between us and the previous participating. Now, that's given that there is a previous participating, because if there isn't, then we can't compete, we just send what we received, which is basically this. So let's check. In that case, we just return this. Else we can compete the minimum between what we received and current difference. Now, the current difference should be absolute, but I don't need to call abs because our array is sorted. So I'm always reducing the smaller number from the bigger number. So even if they're both negative, I'll still get a positive number. So I don't need to call abs. So we called it with us participating. Now what if do I need to add here before calling without us participating? correct. I must check that current n is bigger than k, because if we passed this line because they were equal, then we must participate. Otherwise, there'll be one element missing to get k elements. So only if current n is bigger than k. So now the previous participating is not us, it's what we received, as well as k, as well as the mean diff. We don't compete with it. Once this all folds back to us, we can return, but I don't want to have an overflow. We have to have the modulo. So it's 10 to the power of 9 plus 7. So we return. So this is the naive algorithm. As we saw on paper, it works, but we will stop here to see the TLE. So now we're here, I'm gonna press continue, and you see that it's running and running and running. I'm gonna stop it. Let's remove the breakpoint and add optimization. So in the optimization, we will avoid doing a recursion that we already have done. It will save so many recursions going deeper and deeper. So what is the situation that we can recognize that has happened before? Well, it's getting to the recursion to work on a specific index, having the same previous index as been before, with the same k elements remaining together, with the same indifference found so far. And it will happen having many elements, then with many of them participating and not participating before us. Some of them will not change the situation of how we get to here. They will not have an effect because they didn't have the best difference. And so this is what we're going to have in memoization. This is the situation for which we're going to save a value that we have previously calculated. So since the situation is composed of 4 values, then how will we hold it? Well, I tried different versions. I tried having them in a multi-dimensional array of the index and prev index and k, and then the last, because each of them can be only 50, up to 50, 0 to 50, except for prev index that can be -1, so I just added +1 when I accessed it. So these are all, these 3 dimensions are all of size 50, and these can have different values. So this was just an unordered map, just a hash map for the min diff. So it was an array or a vector of 50, 50, 50 and a hash map. That only beat 23 or so % of the other. I also tried serializing them into a string, just serializing the 4 of them with a space as delimiter. So it was a hash map of string and the value, the sum of powers. That only beat about 63% of others. And what I'm going to show you now is just having a hash map for every stage of it. Hash map for the index, for the previous index, hash map for all of it. That beats about 68% of the others. So it's just slightly better than the strings. And so you can choose. You can choose this whatever you want, or just look at LeetCode for solutions that are so much quicker, but just how can you, really hard to understand, like really you need some math there that, I don't know. This is simple, so I'm just choosing between ways to hash it. So I'm gonna have the unordered map to beat 68 rather than 63%. Okay, so let's declare a using here to not write it twice. So using memoization type, let's call it, is an unordered map of int, that's the key, that will be the index, and the value will be an unordered map of int, that's the prev participating index, an unordered map of int, that's the k, an unordered map where am I? Of int, that's the minimum diff found so far, and the result. This is the data that we're actually hashing, the sum of powers. So let's declare memoization. Send it to the recursion. Send it also here and here. Okay, so let's use it. So what we need to say is, if we know that we need to do the work, let's first check if maybe we have already done it. So I'm going to use contains from CPP20. So I'm going to access all levels and as contains of the end. Now, if the other levels don't exist, it doesn't matter, they'll be added. I'm gonna have to add them anyway. So if mem at index, previous index, k contains min diff, then we can return it. I'll copy paste. Then we return this value because we have it. But if we don't have it, we are just calling the recursion, and before we return, let's feed it to the memoization so that we don't have to calculate it again. Okay? So this is using a memoization. This concludes the code that doesn't get a TLE. Let's run it. Before running it on LeetCode, let's take a second for the time and space complexity. So here we are sorting the input array, which is n log n, but that's negligible compared to the recursion. The recursion, we could say it has the time complexity of 2 to the power of n, because for each element we call the recursion again with it and then without it, and that would be 2 to the power of n unless we had this stop condition. When we reach k equals 0, then we stop. This changes our time complexity to the formula of choosing m elements out of n elements. So that formula is our time complexity and also our space complexity, because we save all these values in the memoization. Let's run this on LeetCode. So it's 69%. It's not horrible, but it's not amazing. The solutions here that really look at my runtime, it's 465 milliseconds. Look at this here, 2.36%, used 29 milliseconds only. That's really a big difference, but they are really, really hard to understand. So if you want a challenge, go ahead. For me, I really prefer the simplicity here, and I hope you liked it too. And thank you for joining me on CPP in Pajamas. See you next time.